Hey everyone, so we're going to continue on with the very last topic of this course, where we're going to talk about diffraction patterns and then also a little bit about polarization. That one's going to be a more of like a very quick and easy thing. As I mentioned before, the things that we're going to talk about with diffraction patterns is going to be very similar to what we talked about with the interference patterns, mainly because they are very similar in how they work. Um, so first, we've talked about how when a wave encounters a boundary, that it will end up bending around it and spreading beyond it. Um, Now, what this ends up telling us is it actually tells us there's a limit to the resolution that optical instruments can actually achieve. Things like, telescopes and microscopes and stuff like that. There is a limit before they won't be able to resolve things. That's what the term resolution means: is the ability to resolve or differentiate two items in space. So, for example, something that has very low resolution would take two very close together stars and see it as one single star rather than two separate stars. So that's what we mean by resolution. Um, so um, we talked about this before, that when waves come towards a surface, it will actually go around it. Well, it turns out that we could do something with this by taking a solid disk and hitting it with a type of light wave, based on it has to be a certain wavelength based off of the size of the disk and the separation from some screen. But what will end up happening is kind of similar to the double slit experiment, where when the two waves came in through those two openings and they kind of started spreading outwards right in the middle of the two slits on the viewing screen, you would actually get the um, constructive interference, the most constructive interference of those two waves interacting. Well, we could do something similar by taking a solid disk and almost doing the opposite. Instead of having the light going through to, like, having two openings in an obstruction, having an obstruction, and the wave will go around it and meet in the middle, just like with the double slit experiment. So it seems really weird. It's actually one of the reasons why uh, it made a lot more sense as we started talking about light as being a wave, because this was a type of an effect that light showed, that you would end up having this bright dot in the middle of this shadow, um, that could not be explained without light being a wave. So again, this kind of ended up solidifying a little bit more and explaining more about why light does what it does. Um, so you'll notice that we create these type of diffraction patterns by placing obstacles in front of light and then seeing how it interacts with itself, and we'll end up getting these ripple effects, these fringe effects, very similar to what we got with the double slit experiment, mainly because, again, it's coming through the same idea that you end up creating two new quote unquote unique waves that are now going to interact with itself, um, and have areas of constructive and destructive interference. Um, so here's just a picture of the solid disk creating a shadow with the bright spot in the middle. All right. So first, what we want to do is just talk very quickly about a diffraction being caused by a single slit. So here we have a slit that has a certain width. We send a single wavelength of light through the slit, and it strikes the screen on the backside. Now we know that as the wave goes through, because of Huygens' principle, that it will eventually start spreading outwards. But right in the center will end up being a very bright spot, and then it will end up being more decreasing intensity as you get further away. Um, and we also know that some of the waves will end up going off on angles. So what it turns out is through diffraction, we end up getting this effect. So we get most of the brightness, most of the intensity of the wave directly in front of the slit, which is what we expect. But it turns out that once again, because of the fact that we can consider each wavefront or all these little areas as being unique waves, it turns out that they'll end up creating these parts of destructive and constructive interference, though at a very, very small scale. So, if you recall, with the double slit experiment, we got these fringes, and the intensity did sort of decrease, but it was a much more gradual decrease. Here, you'll notice that the decrease is very abrupt. You go from having almost 100% intensity to down here is probably somewhere closer to like 5% intensity. A significant drop. So that's what they're kind of showing here is that, uh, we take this as almost a set of individual wavefronts, um, or wave sources. I guess that would be a better choice, wave sources. And just like with the interference, we say that we get constructive interference at, when the distances are full wave integers, and you get destructive interference at half wave integers, and so on, so on. Um, so this is just kind of showing how we could figure out these locations. The equation, this should look very similar. Looks like this: d sine theta equals m lambda, where m is 1, 2, 3, any uh, positive or negative integer. Now, one thing that I want to point out about this is very similar to the equation for the double slit experiment. Of course, what we put in for d is different. For the double slit, the little d was representing the distance between the slits. Well, here this is representing the spacing of the slit. However, there is another very important thing to take from this. The equation for the double slit experiment told us the location of every location of the constructive interference, of all the maximums, all the peaks, all the bright fringes. This equation, on the other hand, actually tells us where the minimums are going to occur. Where do all the destructive interferences occur? So that's one thing to note. If when you record these equations, you need to make sure that you're recording whether they're referring to constructive interference, bright fringes, or are they representing destructive interference, where we get the dark fringes or minimums. All right. So yeah, these are telling us where the minimum locations are. So the first minimum is going to occur at lambda over d, then 2 lambda over d, then 3 lambda, and so on and so on. All right. So here's the first question. You can pause the video, work on this yourself, and we'll go over in a second. All right, so we're just going to plug and chug, but we want to make sure that we end up getting our our units correct. So notice how we have millimeters here, nanometers, and centimeters. So we use the equation. Now they want to know the central maximum, so that first big peak. So in order to figure out its width, we need to find the location of the first minimum and then double that for the second minimum. And then we'll be able to get the full angle as being between that. So we use the equation where we're looking for the first minimum. We get 0.75. Take the inverse sine, we get 49 degrees. Now, one thing to note, you would not be able to do the small angle approximation here. For those who are probably thinking that they could plug in x over 20 in for sine theta and then solve that way, you will not get the correct answer. you have to actually do the full trig function here because our angle here is going to be really, really big. Um, so once we have that, now to figure out this side, um, I do want to point out really quick that this is a slight typo. It wants to know the width in degrees. It should be double this. This is the half width. So it should be 98 degrees. Um, so going from here, we're still going to use the 49 degrees. That way we can use the tangent theta equation to figure out what this side is. When we do that, we get that the width is 46 centimeters because we take that and then double it. All right. I'm just gonna pretty much skip a lot of this because it's talking about the phasor diagram again. So I did mention very briefly that this is something that does come up in other classes. So you it's fine if you want to go and learn about it now, early on, but we're not going to do anything about it. Basically, this is just kind of saying, we can think of this as being a bunch of individual slits and then figuring out the intensity and how the intensity drops along the diagram. So you can go through the notes if you want, or look in the textbook. I'm just going to skip a lot of this stuff. All right. This is actually the one thing that I want to refer to. So, as I said before, for the interference patterns, we did end up getting a lot of these, bright and dark fringes. However, the intensity was somewhat uniform, at least on small scales. So here they say from like 5 degrees to 10 degrees, there really wasn't much of a drop. It was a very gradual drop as you got further away. But here, by the time you get to 5 degrees, it ends up dropping really big. So when you combine these two together, we end up getting pretty much what we would think of when we introduce diffraction into the double slit experiment as well. So this is kind of like overall what we're going to end up getting is, bright, dark, bright, dark. So the interference patterns that we talked about in the previous class were really only half of the discussion because it turns out there actually is a second factor going in there, which is caused by the diffraction of the wave actually being bent as it goes through those openings. Something that we didn't really take into account. So that's pretty much what I think is important to take away from here is that there are two factors in part of these double slits: the interference pattern factor, which doesn't really change its intensity, and the diffraction pattern, which does very dramatically. And it would also explain why the interference in the double slits that we saw had, again, not really that noticeable drop over small distances. Yeah, so you could see here, this would be a double slit, an example of a double slit where you get these fringes, but then all of a sudden there's like almost like a bubble where it kind of goes dark, and then there's fringes again. And here's another one where it's a little bit more frequent. You get a bubble here of intensities, and the next bubble it's a little bit lower intensity and lower and lower and so on and so on. All right, so we're going to talk a little bit about resolution with circular apertures. So here's an example of basically what we would say a low resolution would be. So here is what we would see when we look at something caused by the diffraction pattern of a single point object. So again, we have the rings here. However, if the two objects are very, very close and it's difficult for whatever device we're using to resolve it, what we'd end up getting is pretty much what looks as if it's one single object. So you'll see here and here do kind of look similar. This one's a little bit more oval-like, but basically it's caused by the fact this is caused by two objects being close together and not being able to be resolved by the lens due to the diffraction limit. All right, so for circular lenses, the central maximum, the half width, basically the location of the first minimum, is actually given by this equation. Theta equals 1.22 lambda over d. So where d is going to be representing the diameter of the lens. So again, very similar to the d sine theta equals m lambda equation. So in order for us to resolve two objects, two sources of light, basically we need to make sure that the location of the brightest spot is not overlapping with the other one. Like if we have one intensity here and then the other item is also peaking like over here, then what ends up happening is we'll just get a much larger, because remember the two intensities will combine and we'll just get a much brighter spot in the middle because of all the intensity kind of combining together, but it'll be hard to differentiate it. The only way we can differentiate two items is if one of them, the intensity, is located at the minimum of the other. So here is a quick little diagram of basically the only way that we can differentiate two items. So that half width angle actually tells us the angular distance between the two items that we can resolve, because the minimum of one wave is the location of the maximum of the other. So this is what's called the Rayleigh criterion, basically saying that when we're using some sort of disk and we're using it to resolve an item due to diffraction limits, that they have to be at minimum, the most that they can overlap is half the resolution width of the lens. So basically this again. So this will end up being our angular limit to resolve two items. So here's a question where we're going to be using that limit in order to figure out what the resolution is for this. Notice how they do say something about half an arc second. So you might want to look online, type in Google what half an arc second is. It's a form of an angle. So, look up that and then, pause the video, work on this yourself, and we'll go over in a second. All right, so they say that the Earth-based telescopes have a limit of half an arc second. So half an arc second basically is essentially taking 1 degree and dividing it by 3,600. So that's how you get arc second. One way of thinking about it is like, think of the degree as being, what would it be? An hour. So 1 degree is 1 hour. So divide it by 60, divide it by 60 again to go from minutes to seconds, and that's how you get arc seconds. So half an arc second, and then converting it into radians, we end up getting this. So this is the limit to most Earth-based telescopes due to things like air being in there, diffraction from the air, all that type of stuff, pollution, everything. Now, for the Hubble telescope, we'll use that equation since it's not being affected by that. And when we plug the numbers in, we end up getting 2.8 times 10 to the negative 7 radians. So essentially, the Hubble's telescope is able to has a diffraction power of about 9 times more than the Earth telescopes. All right, here's another question. You can pause the video, work on this yourself, and we'll go over in a second. All right, so here we have two different telescopes. There's a regular telescope here, and then a radio telescope for part B. And we're just going to be using the equation both times. Here, we're going to have to convert this um, into meters. So when we plug the numbers in, we end up getting that the base telescope has a resolution of 1.3 times 10 to the negative 7 radians. And then when we go to the radio telescope, plug the numbers in, we end up getting 1.6 times 10 to the negative 4 radians. So not nearly as good of a resolution, mainly due to the fact that the wavelength is much higher for radio telescopes. And it's one of the reasons why the radio telescopes need to be so large, is because due to the large wavelength, the size needs to be large just to get a decent resolution. So, yeah, this is a actually, I mean, this is not the largest telescope, but you can see here that a regular light telescope uh, needs to resolve much higher than what the radio telescope is. And if this was as big as the radio telescope, it'd be able to resolve even better. All right. Oh, you know what? We're going to leave it at that. We'll talk about diffraction gratings in the next video. You'll notice that these two videos are fairly short, so that's nice. Nice thing to end on. All right. If you have any questions, please let me know. Otherwise, I'll see you later.